It's got plenty of battery. All right.
Now how much that'll hold.
Good to go?
Good to go.
Okay. In the previous class, we talked about how to convert the kind of random vibration into a vibration that has a fixed or constant amplitude, right?
Mm-hmm.
And actually today we will talk about how to convert from here to there. Okay, we will do some practice. Convert. Can you see my handwriting? You may just check the screen.
Should we could move that a little closer? Yeah.
Okay.
Do it.
How convert a random vibration into a vibration with a constant amplitude and a known number of cycles. Okay. Because we can analyze the vibration with a known amplitude and known number of cycles a lot easier than the random vibration. Then we will talk about liquefaction. Okay. This topic, the liquefaction, will wake up Nathan, right?
I'm awake. Just tell me.
Further awake. Okay. Then let's talk about how we can actually convert natural earthquake vibration to a fixed number of cycles and amplitude. Vibration conversion. S-I-O-N. Okay. For this one, you need to get help from the handout. Okay. The handout is old one, very old one. I guess that should be sometime 1970s. Okay. And that is written by Seed, Idris, McDish, and Banerjee. And when you go down to the all the way bottom of the handout, you can see who are those authors, 1, 2, 3, 4. And Seed, it says Professor of Civil Engineering, University of California, Berkeley, California. And what's the nickname of Seed?
Father. No, never mind. It's wrong.
God of Soil Mechanics. Father of Soil Mechanics is
Terzaghi.
Terzaghi. Okay. Then number 3 and number 4, McDish and Banerjee, it says Graduate Research Assistant. Okay. They were the graduate research assistant. Nowadays, they are the seniors in geotechnical engineering. When you go to the geotechnical conferences, especially conferences about soil dynamics and earthquake engineering, those, the Banerjee and McDish are the seniors. So this paper is very old one, but there is classical ones, not just classics, classical ones. That's the reason why you have the copy of those things. Okay. What is the page number for that one?
Just the second page.
Second page.
Okay.
This one is actually one of the actual earthquake recordings, so-called seismograph. Okay. On the x-axis, you can see time. On the y-axis, you can see that is the what? Shear stress. Well, you can just assume this one is the amplitude. It looks like just the random vibration, right? Then how to convert it to the vibration that is easy to analyze? You can go to page 'There should be a wave and table somewhere.
This.
Yeah. Go to page, what is the page number?
17 something, 17. So I have.
On the top right, you may see the page number 166. That is my handwriting. You see that? Do you see it? 166. Okay, let's use this example to solve it in our class. You all got the 166? Just look for my handwriting at the top upper right.
Give 4 pages. That way. Keep going. No, you're right. It's that one.
You find it?
Yep.
So page 166. See at L. Okay? We have this one. Okay. Rule number 1 is base amplitude is (0.65) peak acceleration. Bless you. You got my blessing, so you got to tell me why we picked up 0.65 peak acceleration. Why not just the peak acceleration?
Be conservative.
No. Usually that is the good reason, but not this time. For this one, it looks like this one has the peak acceleration, right? Let's say this one is acceleration, this is time. Peak acceleration, maybe this one is about 50% of the peak acceleration. But again, our base amplitude is 0.65 peak acceleration. The reason is there is actually no good reason.
Just something we convert, something we normalize the...
Yeah, I mean, we are trying to normalize the random vibration to a kind of vibration with fixed amplitude and known number of cycles. But the reason why this one is 0.5 is if we just try to find out the region, there should be something like about the same region as why your name is Corey. Why your name is Corey?
Just what they did.
Yeah. Why the Jimmy's name is Jimmy? Okay. Actually, when you read this handout, you can find out, hey, I don't like the 0.65. I want to use 0.85. That's fine. Okay. That's fine. Okay. I will revisit why 0.85 or 0.5, 0.75 is fine. But again, we will use 0.65 because Corey's name is already Corey. We are not going to rename Corey to Cray. If we rename his name to Cray, then you can write probably by a lawyer, and probably he can change your name to Cray officially, right? But we are not going to do it because your current name is just
Already there.
already there, and we all know your name as Corey. Again, same thing. This 0.65 is, again, this is same as Corey. This number is already there. And everybody is using this number, not 75, not 85. Okay. Then follow the procedure in page 166. Okay. In page 166, okay, what you need to do is, okay, you can see those waveform and you can see those horizontal lines, correct? In the recorded waveform. And in here, you can see the peak acceleration is what?
0.1060.
0.1060. Then okay, that is actually, that should be equivalent to tau max here, because acceleration is what? Acceleration is the quantity that will cause shear stress in the soil. I mean, when you have the vibration, it will cause the stress in the soil. That stress should be proportional to the acceleration. So in here, let's see, okay, here, tau max, that should be really the same as a peak acceleration. How many cycles do we have in here for the peak acceleration? In the waveform, how many number of cycles do we have?
A lot.
A lot?
Cycles?
Just in the peak,
Just the peak?
just one.
Just one.
Yeah.
That's the reason why in this table it has number of cycles 1. Okay. Conversion factor 3. Okay. Again, at this moment we don't know. You don't know why the conversion factor is 3 yet, but we will talk about why that is 3 a little bit later. Okay. Then try to find out the acceleration that is 95% the peak acceleration. How many cycles do we have?
Below 95?
95% peak acceleration.
9.
Huh? We don't have the peak acceleration somewhere 95%. 95% should be somewhere 0.095, right? We don't have that kind of vibration in here. That's the reason why the number of cycles in here is 0. Okay, the bar is really 0. Then try to find out the vibration that has 90% the peak amplitude. 90% should be somewhere 0.09. How many number of cycles do we have? 0 again, right? Now you are following me, 0 again. Then let's find out the vibration that has 85% peak acceleration. So the actual acceleration should be 0.085 or somewhere there. 0.085. How many number of vibrations do we have?
0.
0. Do you see 0?
Above the axis.
Yeah.
Yeah.
So now you know how to follow this figure. Okay, then let's go down all the way. Here there's the number 1, 0.6. Okay, 0.6 peak acceleration, there should be equivalent to somewhere 0.06 or maybe a little bit higher. Can you locate that vibration here? Okay, you found it. All of you, okay, you got it. Somewhere 0.06 or a little bit higher G. Did you find it? Huh?
That one?
Yeah. So it looks like all of us found out that vibration. How many number of cycles? One. Okay, then let's say 55% peak acceleration. I think that should be right. The next one to the 0.6 times the peak acceleration, right? So we have another one. Okay. You just follow this table like that, and somewhere very bottom it shows that the 0.35 tau max. Okay. So the peak the acceleration should be somewhere 0.035 or maybe a little bit higher.
So is this table a given, like this is what you follow, or is this what you make up?
This is a table that you got to follow.
Okay.
Okay. And the acceleration 0.035 or a little bit higher. It says 2 cycles. Let's try to find out where we have those 2 cycles. 0.035 or a little bit higher.
The two right ones.
To the right of the peak one.
To the right of the peak one. Yeah. Oh yeah. Looks like he did not sleep. Jimmy did not sleep. Okay. We have those 2 number of cycles. Just write the peak vibration. So we have 2 number of cycles. Okay. Then conversion factors. I would say the first one is number of stress cycles. Number of stress cycles. Then conversion factor.
So you always stop at 0.35 of tau max?
Yeah. After 0.35, we say no effect. Or maybe we can say negligible effect.
So what took this data, the seismograph?
Oh, this is the
Seismograph.
actual seismograph, actual earthquake record. Somewhere at the top it says San Jose earthquake record, 1955.
So is this how they're trying to compute the magnitude, or what are they trying to?
From this one, you can you can get the magnitude, but at this moment, magnitude is just a number.
Doesn't matter.
Okay, that the general public may want to know the magnitude, but for our case, geotechnical engineers, we really want to know how much damage it will cause. Okay. Then those conversion factors should be found in somewhere earlier. Earlier pages. Oh yeah. Okay. On my, there should be somewhere 4th or 5th one. To the upper right, with my handwriting, it should say 156. Okay, 156. Do you see it? Okay. This one is 156. Okay. Let's follow this figure. On the x-axis, on the far left side, the number of cycles is what? 1. Okay. And this one is the peak amplitude. Okay. the peak amplitude for this case was 0.025, 0.325, somewhere around there.
Oh, they sit in the same ones.
Number of cycles 1, and go all the way up there, and your amplitude is somewhere 0.025, correct?
3.5?
So
0.325, somewhere around there. Just look at this one. This point is what? Number of cycles is 1, and the amplitude is 0.325. Okay. Then let's go to the amplitude that is 65% the peak amplitude. Try to get the 0.65 peak amplitude. What should be that number? You can do the quick calculation. 0.325 times 0.65. Hmm? No, it's just the 0.325 times 0.65. You don't have the number quoted.
0.211.
0.211. Okay.
And that's when we multiplied 0.325 times 0.65.
Mm-hmm.
Okay, wait a minute. Yeah, that number is 0.211. So I. Okay. Yeah, take time. Okay, then look at this chart. 0.21 is somewhere there. Okay, and go to the right horizontally and meet the curve, and then try to go down all the way to our x-axis. Our x-axis. Then what's the number of cycles there?
Maybe like 2.75.
No,
Something.
that's like way up there. 2 point.
Let's try to be a little bit easy. Make it easy.
3.
3.
3. Okay. 3.
So in the case of guessing that number, would it be better to round up and down?
You
To be
don't
more
have to.
conservative?
You don't have to make it round up, but you can do that. But if you are quite sure that number is 0. Let's say 85782, you can use that number, but there's not much point. It will be always easy to just use a simple number. Okay. Okay, that means, okay, one peak amplitude. Again, one peak amplitude will be equivalent, okay, I should say this one. One cycle of peak amplitude should be equivalent to the 3 cycles of 0.65 peak amplitude. Do you buy the idea? You got your windows open last night?
No.
Some of them.
So, yeah.
Okay.
165 was the first.
Since Jimmy was out for whatever his meal or whatever reason, let me go through this one again, because if you don't understand this one, you cannot understand the rest of the materials. Okay. 156.
Thank you.
In this figure, okay, we are trying to find out so-called the conversion factor. Jimmy, you can write it down. Let me explain it one more time. In this figure, x-axis is the number of cycles that cause the liquefaction. And on the y-axis is just the acceleration. Forget about the peak, whatever stress or whatever, just assume this is the acceleration. Okay? And this one is the peak acceleration. Okay? So this point means we have peak acceleration 1 cycle. Okay. Then we are trying to find out, hey, if we take 0.65 peak acceleration, that should be somewhere there, then how many equivalent cycles it should be? Okay. 1 peak acceleration should be equivalent to 0.65 acceleration, and number of cycles should be somewhere 3. Again, that means the damage of 1 peak acceleration will be about the same as the damage caused by 3 cycles of 0.65 peak acceleration. Okay, that means 1 peak acceleration is equivalent to 3 cycles of 0.65 peak acceleration. So this table is really the table that shows the conversion factor. Okay. Then let's go back to the previous table. Was it 166? 166. Okay. And at the bottom of the table, it says 0.35. Okay, 0.35. Then using this table 156, let's try to compute how many cycles it should be, or conversion factor. 0.35 times 0.325. What is that number? Hmm?
0.114.
0.114? 0.114. Somewhere 114 means
Gonna be like right
very
here.
close to 10, right? Then what is the equivalent number of cycles? You go this way,
Call it 200.
somewhere, maybe it looks like somewhere 200. Okay, it's somewhere 200. But the number shown in here is 2. Something is wrong.
Maybe we don't have enough knowledge yet.
We have enough knowledge, but it's not wrong. Okay. The only problem is, if we say the peak amplitude is the base, if that is the base, then number of cycles in this table should be somewhere 200. But again, our base is 0.65 peak acceleration. Your name is Corey, not Craig, right? our base is this one. This is the base. If we switch the base, then what we will do is, okay, in this table, this point is our base. Then when we readjust, okay, I mean somewhere here, in here you can see, okay, 0.65 conversion factor is 1. Even though it did not write it down, there is 1. 0.6, that is close to 1, but it shows just 1. Do you see it? Okay, if we say 0.6 and conversion factor is 3, then the number for the 0.35 should be somewhere 200. But again, our standard or base is 0.6 should be 1, then 0.35 will be 2. Are you following me?
We could go over that again.
Okay,
So does this represent the, no, this doesn't represent the 3 cycles.
wait a minute. The number of, oh yeah, I was wrong. Number of stress cycles, those are actually number of cycles that we can find here. Probably, I was wrong, okay. I was confused. Okay. Conversion factor is, okay, yeah. When 0.65, our conversion factor this one should be 1. Okay, 0.6, it says 0.7, the 1 in here. This number will be 1, 0.65. Okay.
All those are 1s?
Huh? No, not
Just
1.
that number?
Just
Okay.
the number at 0.65. Yeah, this number will be 1.
Okay.
Okay. That is 1. And okay, again, if we convert this one as 1, then the number for 0.35 will be,
200.
it's not really 200. Okay. When you can see, when the amplitude is high. Okay. I know it's confusing, so let's take maybe about a minute to think about overall concept. Then I will continue my lecture.
So how did they get 0.02?
We will just think about those things, and we will talk about that a little bit later. I'm trying to find out easier table. There should be an easier one. Okay, then let me continue my lecture. Again, this figure 156 shows that again. 1 cycles of peak acceleration should be equivalent to 3 cycles of 0.65 peak acceleration. We buy that idea. And then what we can know is, okay, as the amplitude is getting lower and lower, it requires higher and higher number of cycles to cause the liquefaction. Correct? That means, okay, let's say one cycle of low amplitude, let's say one cycle of 0.1 peak acceleration may require 1,000 number of cycles to cause the liquefaction. Okay? So effect of low amplitude vibration will be very minimal. Then we can say, okay, if we require just one cycle to cause a liquefaction, that is the 0.65 peak acceleration. Then we can say effect of 0.1 times peak acceleration will be 0.1, 0.001, 0.0001, something like that. Do you buy the idea? Okay. Then let's go to the wait, this is page 165. Go to page 165. And 160. Is it 160? Yeah, 165. This one, the one that has this one. That shows figure 7. Yeah. Okay. Then this figure will show actually the equivalent number of cycles, proper equivalent number of cycles. Again, 0.65 is the base. So when you look at the 0.65, go horizontally and meet the curve, and going down, what is the number there on the x-axis? 1. Okay. So 0.65 is the base one. So one cycle, and go to the peak one in here. Peak one is on the x-axis. There should be 1. What's the number of cycles?
3.
3. Okay. One peak vibration is again equal to the 3 number of cycles for 0.65 times the peak acceleration. Then let's say 0.4. Okay. When y-axis is 0.4, try to find out the equivalent number of cycles.
0.1.
Somewhere point,
0.02.
somewhere around there. Okay. It may not be very accurate, but just use this chart, find out the equivalent number of cycles. Or this one should be the so-called conversion factor, those numbers. Okay, and then let's go to the 166. Now the lowest number of cycles in here is 0.35 in the previous table, 0.35. Then try to find out the equivalent number of cycles. Somewhere around 0.02, correct? And again, using this chart, figure 7, let's try to find out the conversion factor from 0.55 tau max, 0.55. Which number do you have?
Close to 0.3, 0.35.
Okay.
Yeah, 0.4.
Then, I mean, if you can pick up 0.3, that is also a good number.
0.4.
Okay. You can see 0.3, 0.4 from the chart. Which number do you have, Corey? You don't have to be very accurate.
0.5, that's halfway in between them. So you get another half bump.
0.3. Okay, then probably the number in here it says 0.4 may not be the correct number, but we don't care whether that is 0.35, 0.4, 0.3. You can use your best eye inspection, then get the number. Then what we need to do is make the summation of the equivalent number of cycles. That means when we replot the equivalent earth-peak vibration, we can say our acceleration is 0.65 peak. Okay, let's say this number is 6. Okay, if the equivalent number of cycles is 6, that means we will convert the earth-peak record into this way. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Yes. So now I guess we know how to obtain the equivalent number of cycles or equivalent vibrations.
But why did you do 6 cycles again?
Oh, let's say, for example, let's say this
that was an
result
example.
gave us
Okay.
the 6.
Oh, okay.
Okay, just for example. Okay. And some comments. This technique was and is widely used. Okay, again, the reason is it's a lot easier to analyze the wave, sinusoidal wave, with all the same amplitude. Okay? But nowadays, analysis technique is advanced, so that we can analyze the recorded earthquake waveforms as is. recorded waveforms as is means we can just directly use this waveform. Why we could not do that in the past? Using the direct wave requires a lot of calculation. In the past, most calculations were done by hand calculation. So we need to simplify. But nowadays, we got the guy named computer. The computer can just handle the waveform as is. Okay. So again, nowadays, this technique is used, especially when you got to do the analysis just with your hand and in your office. If you have a proper software, then you can use the Ørsted waveform as is.
Is that like the FFT stuff where it converts?
Yeah. Okay. So now at least how we can process the Ørsted wave to do the hand calculations. Okay. And then we will talk about Ørsted and associated liquefaction.
Corey's head's in the way.
First of all, the definition of the earthquake is this one. With the equation, that is this one. We say, okay, effective stress is what? Total stress, huh?
Times the
Not times, minus pore pressure. Or you may recall it, total stress is effective stress plus pore pressure. This symbol is summation. That's the reason why we call it total stress. Okay. But we will use the first equation. Effective stress is total stress minus pore pressure. Particularly for sand. For sand. We know that shear strength of sand is C prime plus sigma prime tangent P prime in terms of effective stress. And this cohesion for sandy soils is what? 0 or negligible. That means our shear strength for sand can be expressed sigma prime tangent P prime. Okay. When we have liquefaction by some kind of strange mechanism, what happens is, okay, what happens is this pore pressure will increase. It will be increased. Then magnitude of this pore pressure will be about the same as this guy, total stress. Then what happens to the effective stress?
0.
0. Pore pressure will rise up and effective stress will be or approximately the same as 0. That means what happened to our shear strength?
0.
0 again. what is the typical material that has shear strength 0? Which material has 0 shear strength? Water or whatever liquid you have. Liquid cannot take any shear strength. And that means or you can say fluid. Actually, fluid and liquid are not exactly the same, but we can say shear strength 0 should be liquid or fluid. And physical meaning is, okay, when you have liquefaction, then your shear strength will be 0, and your material or your sand will behave just like the liquid or fluid. And our sand will behave just like a certain liquid. That means, let's say you have your foundation here for a big building. Let's say a big casino building in somewhere in 2 kilo area. You are playing casino, there is the jackpot machine there, you are playing, stool is there, you are sitting there, you are playing casino, and you got earthquake vibration. This way vibration or this way vibration, then we know that there are a lot of loose sandy materials in Tunica area. A lot loose sand in Tunica area, and usually water table is high because of the Mississippi River just right to the next door, and it becomes what those loose sand materials will behave just like the liquid. Then physical condition will change into this way. You have your casino building. Your condition will be, okay, those sand materials will just change its condition to water. Okay. If this condition happens, your tall building will be a tall ship on the water. What happens if we have a tall ship on the water?
Yes. It's gonna fall.
It will fall, right? Then that will be the really catastrophic failure. Okay. The building should stand upright, right? If this building fall this way or tilt this way, whatever way, that will cause a complete failure. Then let's think about what caused the liquefaction when we have earthquake vibration. Liquefaction. Okay. Probably you saw this figure many different times, but again, I will go over this one more time. I'm plotting the figure that represents loosest condition of the sandy soils. Okay. It's the saturated sand. Okay. saturated sand. Okay. Then let's say this saturated sand is subjected to vibration. This kind of vibration. Okay. You saw this one sometime back, right? This is the initial condition. And again, that's the saturated condition. Then when we have quite high amplitude, that we have relative movement of those particles. Then those particles will try to, there is the water in between those particles, okay, water there. And this wave motion will try to squeeze out the pore water. Squeeze out means it will try to pressurize the pore water, and pore water try to escape from the pressurized place. Okay. Then what happens is, okay, from this condition, it will try to change to this condition, so that pore water will be pressurized and try to escape. It will try to escape. And then you may think, hey, yeah, it's the sand, pore pressure can be pressurized, and it can just escape. Nothing wrong. Okay. But what's going on in real life is, we know that earthquake vibration is actual vibration. It's not this kind of slow movement. It's very quick movement. Okay, very quick. That means, okay, those pressurized water may not have proper path to dissipate, to flow out, to escape. If it does not have proper path to dissipate, then what happens? Huh? It will build up, or let's think about Jim is really mad to Corey. So he just punched on the face of Corey.
Sorry.
Quickly he punched somewhere here. Then probably you can think of two different scenarios. One is he punched him, but very slowly or gently. Then probably nothing will happen, right? Then another scenario is he punched Corey real hard. Then what happened to Corey's maybe chin or face?
Liquefies.
Liquefies means, okay. Your face will be pressurized. Okay. The harder, the higher pressurized, right? The harder the punch is, the higher the pressure will be. And the pressure in the blood vessel may be very high. Then what may happen is it will tear off the blood vessels. Then it may come out to the surface. Okay. That phenomenon is the liquefaction for the soils. Earthquake vibration causes the quite high frequency vibrations. Okay, there should be relatively higher vibration, so that the pressurized water is not properly allowed to dissipate. Then the pressurized water come out through whatever place they can find the path. If somebody hit us very hard, we know that our face will be bloody, right? Okay. Bloody face means it failed and you lost. Okay. That is the this behavior. Try to escape if the core water pressure is high enough, it will find a new path. New path. That means it may find out, it may break new cracks to escape. Okay. New path to escape. And that is very easy for those pore pressure to find out the new path because this process is easy because total stress is, effective stress is total stress minus pore pressure. Okay. If this guy is high enough, pressure is high enough, then this magnitude will be about the same as this one, and this guy will be 0. When this guy is 0 or close to 0, that means you have very low strength materials like the fluid. It's really easy to open the new path. Okay? Typically, we have sand boils at the surface. Again, when somebody hit us really hard, our face will be bloody. That blood will come from some place, not everywhere, maybe a couple of different places. Let's say those places that we have blood, we will call it sand boils. Instead of blood boil, we will call it sand boils for civil engineering. Okay, remember, bloody fish. Okay? That is the reason why we are searching for the trace of sand boils to find out the trace of liquefaction. Okay. When you have a liquefaction, that is usually somewhere, let's say 5 feet down there, 10 feet down there. We don't see it, but at the surface, we usually have sand boils. Probably Nathan remembered why we went out to the field to find out some of the sand boils. Okay. And I think it's about the time. Well, is it about the time? Mm-hmm.
How long does it take the pore water pressure to dissipate?
Huh?
How long does it take pore water pressure to dissipate? Like hours, days?
It depends. If your soil has very high permeability, it's not going to take a long time. If your soil has mostly clayey soils, it will take a long time to dissipate. Yes.
Well, how do you, I guess, determine the magnitude of the liquefaction, or is it just, you just say liquefaction occurred?
There is no magnitude of liquefaction, okay? Because liquefaction is the condition when this guy is high enough and this guy will close to 0. Okay. I understand your question. If this one is high but not very high, so that this one is still not 0, okay, then it's not called liquefaction, but it may still cause the troubles.
So that has to be right at 0 for it. So.
Yeah, liquefaction itself means effective stress should be 0 or almost 0. But again, if let's say your effective stress drops down to 50%, the original effective stress, maybe we can say liquefaction magnitude is, let's say, 0.5 or whatever, but we don't use that terminology. Okay. Let me see whether you have
Wouldn't that be termed more liquefaction potential instead of magnitude? Isn't that fair?
okay. Again, that is the legitimate question. But when we say liquefaction potential, we say there is the liquefaction potential or there is no liquefaction potential. It's 1 over 0 concept. But you may develop your own idea. Hey, liquefaction potential for this case is 0.5, for this case 0.8, for this case maybe 0.1, something like that. But current definition of liquefaction potential is 1 over 0. But it's not really very scientific, but that is the current established. Your homework is this one. Okay. You already have this waveform in your note, correct? Okay. From this one, find out number of equivalent cycles. Again, probably the one that have in your note will be different from the one you have. So all your answers could be different. Just use the waveform that you know that in your note.
That I drew?
Mhm.
It's not
Horrible.
Yeah, that's fine. Just use this one. So if that is horrible, that is really good example. But this one is not very horrible.
So how would we plot
Yeah.
it like they did? Just assume our
Yeah.
peak ground acceleration is a number, state our
Yeah,
assumption?
this one is your peak ground acceleration. Then just follow the same procedure as in the, I guess, 166, right? Yeah.
I had a question about this. This is for a certain type of sand, so did they make